Hi everyone. We're going to continue looking at hypothesis testing in this video. In the first part of this hypothesis testing set, we looked at the null hypothesis and the alternative hypothesis, when we need a one-tailed and a two-tailed test, what the significance level is, and how we conclude a hypothesis test by saying if we're in the critical region or the acceptance region. The main topic here is to link all those things together, as well as talk about how we actually find the critical region using the binomial distribution tables in the formula book. So this is what we're going to go over. We'll go over setting up a hypothesis test. A lot of this will be familiar to you if you've looked at the first lesson. We'll go over finding the critical region. This is all about using the binomial distribution and the tables in the formula book. We'll have a look specifically at two-tailed tests because they're a little bit more difficult, finding the actual significance level, which is quite straightforward, and we'll finish off with a practice question at the end. So how do we set up a hypothesis test? I've been through this in the binomial distribution, but always write down the distribution. It's just a really easy thing to do, and it sets you on the right track for the question. Write down your hypotheses, the null and the alternative. Write down what your significance level is, and write down whether we're going to have a one-tailed test or a two-tailed test. You'll be able to see that by looking at the alternative hypothesis. If your alternative hypothesis has a larger than sign or a less than sign, it's going to be one-tailed. If it's got a not equal to sign, it's going to be two-tailed. Okay, so look at your alternative hypothesis. That'll tell you whether we have a one-tailed test or a two-tailed test. In a one-tailed test, we only have one critical region. In a two-tail, we actually have two, one on each side. So how do we go about finding the critical region? We're going to make use of the binomial distribution tables. So we don't actually have to use the binomial distribution formula, which I'm sure everyone will be very happy about because it's quite complicated. We can just use the tables. So whenever we do a question on hypothesis testing, they will always give you values of n and p for the binomial that can be looked up in the table. So there won't be any that you can't look up in the table. So let's do an example. Most suspects a coin lands on heads less often than a fair coin would. And then a coin's tossed 30 times to test that suspicion, and we want to find the critical region. So we're going to go through what we said we'd do to set up the hypothesis test. First things first, let's write down, let's come up with a random variable, a discrete random variable. We're going to call it x. That's going to represent the number of times the coin lands on heads. We're going to write down our distribution. X is binomially distributed, and remember this first number that goes in the distribution is n, the number of trials. You can see that there. We throw the coin 30 times. The second number is p, which is the probability of success. Now we're assuming here, we take the kind of expected probability of success here. So this is effectively from the null hypothesis. Okay, so this is from the null hypothesis. So we're assuming the coin's fair, even though we've got a suspicion that it might not be. Okay, so we take the probability of success from the null hypothesis. We can now start writing down our hypotheses. So H0, the null hypothesis, is that the coin's fair. That's the original assumption. Our alternative hypothesis, H1, is that it lands on heads less often. Yeah, lands on heads less often. This is H1 than a fair coin would. Okay, so we're saying that P is actually less than 0.5, and that's our alternative hypothesis. That's the suspicion about this coin. We're then going to say whether this is a one-tailed or a two-tailed test. Notice that we've got a less than sign, so it must be one-tailed. Okay, if it had been a not equal to sign, we'd have a two-tailed test. Okay, and just make a note of the significance level from the question, and you'll always be given this in the question. It's 5%. So let's go ahead and try and find this critical region then. From the question, we had n is 30 and p is 0.5. So I'm going to go ahead and find that table from the formula book. So I've gone through the formula book and I've found the table for n is 30. And I'm then going to find the right column for p is 0.5, which is this one here. Okay, so we know which column we need to be in. Right, now what we do here is we remember what our significance level was. Our significance level was 5%. and we had a less than sign. Remember that our H1 was that P is less than 0.5. So what we're going to do, if we have a less than sign, we're going to start from the bottom of the table, of that column, and we're going to work our way up until we see a number that is less than 5%. So we keep working our way up until we see this value here, which is 4.94%. Okay? So we're always looking, well, not always, sorry. We in this example, we're looking for a number that's less than the significance level. They will tell you in the question whether they want you to go less than the significance level or as near as possible to the significance level. If they don't say anything, assume it means less than the significance level. So in this case, we were looking for the first number that's less than 5%. Okay, so we found the row which has a probability of less than 5%. And this row, remember, is the probability x is less than or equal to 10, if you remember how the binomial tables work. That means we've got a critical region that x is less than or equal to 10. So we found our critical region there. If we throw this coin 30 times and it lands on heads 10 times or less, we're in the critical region and we'd reject the null hypothesis. Hopefully you remember how we make those conclusions from the first part on hypothesis testing. If we're in the critical region, we're going to reject the null hypothesis because it seems quite unlikely that it's correct. Let's have a look at another example. So a manager at a store knows that in a previous month, 45% of customers bought medium-sized clothes. She thinks this proportion has increased. That gives you a clue as to what the alternative hypothesis is going to be. Take a sample to investigate, find the critical region at 1% level of significance. So this time we've got let x be the number of customers who buy medium-sized clothes. So we're just declaring, you don't have to do this, but it just kind of reminds you what we're talking about for the question. This is our discrete random variable. It's the number of customers who buy medium-sized clothes out of the sample. We can now write our distribution. This is n, remember, and we get that from here. This is P. Remember, we take this from the null hypothesis. It's our original assumption about the data, and our original assumption is going to be from the previous month. 45% of customers buy medium-sized clothes. There's our null hypothesis we just talked about. And our alternative hypothesis, we've said she thinks this proportion has increased, and therefore H1 is that P is larger than 0.45, so the proportion has increased from what it was in the previous month. It's got a larger than sign, so it's going to be a one-tailed test, isn't it? The only way we get a two-tailed test is if it's a not equal to sign. And finally, make a note of the significance level from the question. It's a 1% level of significance. Now we're going to find that critical region. Remember, n was 20, p was 0.45, and we had 1% significance level. And remember that our alternative hypothesis was that H1 is P is larger than 0.45. Because it's larger than, we're going to use the table slightly differently. First of all, find the table with n is 25, and find the column for P is 0.45. Because we've got a larger than sign here, we're going to start from the top of the table. Now, before we started from the bottom of the table, that's because we had a less than sign. Because we got a larger than sign, we need to look down the table. And what we're going to do is we're going to look for the value, the first value that is larger than 1 minus the significance level. So actually, we're going to look up 99%, or 1 minus 1%. Hopefully that makes sense. Because we're going up the table this time, instead of looking for 1%, we're going to look for 99%. If we had a 5% significance level, we'd be looking at 95% in the table. So we work our way down until we find a value that's larger than 99%. And there it is. Okay, so you can see in the blue highlighted column, we've got 99.42% there. Okay, and that is the probability x is less than or equal to 17. Okay, now that is not our critical region. We're expecting the critical region to be at the top here. If this is our 0 to 25, our critical region is going to be up here somewhere. It's going to be the last bit where we say if it's this high, then actually, yeah, P is probably larger than 0.45 and more people than we expected buy medium clothes. So we need to kind of flip this on its head. Actually, the critical region is this bit at the bottom here. This is the critical region. Now, to do that, we need to flip the probability round. So we actually have 1 minus the probability x is less than or equal to 17 is 1 minus 0.9942, which gives us less than 1% as we required. So this is less than 1%, which was the significance level. Okay, so actually the critical region is x is larger than or equal to 18. This might seem a little bit complicated, and it is quite tricky to understand. The best way to think about it is that it's the area underneath, it's at the area at the bottom here that's the critical region. The bit I've drawn a bracket around here is the critical region. So it's x is 18 and above. We don't include 17 because it's just below the critical region. So another way of remembering is find your critical, find the number 17, and then add 1 to it, and it's x is larger than or equal to that number. That's your critical region if you have a larger than sign in your alternative hypothesis. Remember, if it's a less than sign, we're looking up here for a critical region. We just read off the first number that's less than our significance level, and that is the critical region. So what about in two-tailed test? So we said find the critical region for a two-tailed test with p is 0.35, n is 20, at a significance level of 10%. The probability of rejection in each tail should be as near as possible to 5%. Now here's the key part with two-tailed tests. If we have a significance level of 10%, a two-tailed test has got two critical regions. Now each of those can't have 10% probability. Otherwise we actually have a significance level of 20% because they add together. We have to half our significance level. Okay? We half the significance level, and half of it will go in the first part of the critical region, half will go in the second part. Okay, so actually we'll end up with something that looks like this. Two critical regions, one here, one here. Each of those will have about, or as near as possible as the question says, 5% in each. Okay, we have to half that significance level. If our total significance level is only 5%, we'd have to half that and put 2.5% in each of the sides, each of the critical regions. Okay, so in a two-tailed test, we have to half that significance level. Write down your distribution and the hypotheses. Now, we've actually been told that it's a two-tailed test, so it must be a not equal to sign. Because it's two-tailed, it must be a not equals to. That's the only way you get a two-tailed test. Otherwise, we'd have a less than or a more than sign. It would be one-tailed. And we said the significance level is 10%. Let's bring in the table now and have a look. So I'm going to bring in the table for n is 20, and I'm going to look at p is 0.35. Okay, now there's going to be two parts to this critical region. There's going to be one part at the top of the table up here, and one part at the bottom of the table down here. We get a critical region on each side, as I tried to show you in the previous page. So we're going to look for, remember we've got 5% on each side. Okay, we half that 10%. So what we're going to do is look down this column until we see a number that's as close as possible to 5%. Hopefully you can see it's that one there, that 0.0444. That is 4.44%. Okay. The next one's 11%, so the 4 is the nearest possible. That row is the nearest possible. And that is x is less than or equal to 3. That forms part of our critical region. And now to find the other side of the critical region, we start at the bottom of the table and work our way. Oh, apologies, I've done this the wrong way around. We look down the table now until we see a number larger than 1 minus the significance level. So we were looking at 5% here. Now we're looking for 95%. So we're going to look for the number that's nearest to 95%, and hopefully you can see it's here. This 94.68% is the other side of the critical region. That way both ones are as near to 5% as possible. The probability of rejection, which is the bit above or below it, is as near to 5% as possible. So this one was x is less than or equal to 10. And remember, for this bottom bit, this is the critical region here, which is x is larger than or equal to 11. So we always add 1 to it because that's the critical region at the bottom. The reason is because we have to do this 1 minus, we have to flip the probability round to make it work. But if you struggle to understand that, just think about adding 1 on if we're at the bottom of the table. If your critical region is at the top, we have a larger than sign. We need to add 1 on, so we've got x is larger than or equal to 11. So our critical region is x is less than or equal to 3, or x is larger than or equal to 11. There's 2 parts of the critical region. One here, and one here. Okay, they're the 2 parts. So we're looking for the number that's as near to 5% as possible, and as near to 95% as possible. If our total significance level was only 1%, say, we'd have to have 0.5% on each side, just as an example. So we'd go down and look for one that's as near to 0.5%. It's going to be this one here, and as near to 99.5%, which is this one here. And we get a different critical region. Okay, so the critical region is dependent on our significance level.